Okay, great. Our next speaker is James Reuther. He's the Deputy Associate Administrator for Programs in the Space Technology Mission Directorate. James is going to speak to us about STMD interests in CubeSats and this CubeQuest challenge. And so, James, I'm going to turn it over to you, and then we'll give you a break in when there's a 5-minute warning, and then you can take questions, and if you can't hear the questions over the speakerphone, I'll relay the questions to you. Okay?
Yeah, I think I'm going to have trouble with the questions, hearing the questions, just because, as I was listening in here, I could barely hear any of them. So it would be great if you could relay. I'm going to probably take a short period of time and make sure that we've got time for questions. I think we scheduled for 15 minutes, including questions. So I'm just going to get right to it. I do not have any charts or anything. This is just a quick discussion. I was asked to present what is STMD's interest in small spacecraft in general, and also what is the interest specifically in the CubeQuest challenge that we're sponsoring out of the Centennial Challenges. So the Space Technology Mission Directorate, which is one of the 4 mission directorates within NASA and is new in terms of all the other mission directorates. It's only been around in one form or another for about 5 years, and then as a standalone mission directorate only for about 3. We're the newest NASA mission directorate, and we're focused on space technology development and demonstration, taking technology all the way from the low TRL standpoint all the way up through getting them demonstrated in space and into utilization, or as we say, infusion of those technologies. That's everything we do. In the area of small spacecraft, we actually have one of our 9 space technology programs, the Small Spacecraft Technology Program, specifically geared to look at technologies in the small spacecraft area. And our motivation is clearly to create a program and look at small spacecraft in general, is the reality that small spacecraft are an emerging capability, an emerging marketplace, and in the future will likely have many utilizations or fitting the capability needs for many applications that have traditionally maybe been done by large spacecraft. So to that end, the small spacecraft program is looking at 3 different principles that it's after. The first is trying to demonstrate that small spacecraft are actually capable of performing missions that maybe large spacecraft currently are performing, or performing entirely new missions that could not be performed by a single monolithic spacecraft, larger spacecraft. And so it is essentially trying to expand the market space for small spacecraft with the idea that it is a far more affordable and accessible way of actually performing space missions in the future. So that's the first principle that we look at. The second principle is to realize that while small spacecraft are an emerging capability, not necessarily all of their capabilities are up to par with what can be done with large, expensive spacecraft today. And so in many places, those are technology hurdles. So our principle in this case is to invest in technologies that will enable small spacecraft to be more capable than they currently are today. And there's a 2-part to that effort or principle. The second is the realization that small spacecraft are in some ways the ideal, most affordable test bed for new technologies, whether they be applicable to small spacecraft themselves or in many cases applicable to larger key point that we are trying to advance technologies that will specifically enable small spacecraft in the future. And then the final tenet or principle within our small spacecraft program is to realize that using small spacecraft to energize the aerospace industry and the space industry in the future is probably a very important aspect to maintain. And in this regard, we actually look towards how can we get small spacecraft into the hands of university students or university developers, where it's often impossible for people early in their space enterprise careers to get involved in a very large, expensive mission, other than doing maybe a very minor role. This, by utilizing small spacecraft, you could get new entrants into the space community involved for a very affordable cost relative to larger spacecraft, and therefore it is an ideal launch point, if you will, for new entities, new private citizens, new students to get involved in space, whether that be in small spacecraft in general or in larger aspects of the aerospace enterprise. So that's the reasons why we invested in small spacecraft and have a technology program called the Small Spacecraft Technology Program to leverage that. And if you look at the CubeSat challenge itself, it actually fits very well with that second tenet or principle that I brought up. In other words, it's widely recognized that if you try to take small spacecraft, which have become ubiquitous in low Earth orbit, and want to perform missions away from low Earth orbit to distant destinations, challenges immediately emerge. And the two biggest challenges, at least that we have seen from the Space Technology Mission Directorate perspective, is propulsion and communications. Propulsion, just because you end up having to carry the mass of the propulsion system and the propellant with you, and when you're trying to fit into a CubeSat and you want to have a significant delta P, it turns into a significant challenge. Communications, because the power required as you get to further distances, say especially away from low Earth orbit, and you want to have significant communication bandwidth, or a significant communication bandwidth capability, it becomes very challenging because of the power limitations that are constrained by the small platform that you're on. And so tackling those challenges, we think, will highly enable small spacecraft in the future to be able to perform a much greater diversity of missions. And we think that these more compact, more efficient communication methods and propulsion ideas would translate actually into utility even on larger spacecraft as well. So it serves both as a portable testbed platform as well as technology specifically geared getting small spacecraft to be more capable in the future. So that's really all I wanted to say. I hope that gives the context of why Space Technology Mission Directorate is interested in small spacecraft and what we're after, and also why we've decided to put in place this hopefully exciting Centennial Challenge.
Thanks,
and I'm happy to take any questions for 5 minutes.
Thanks, James, and I'll relay the questions to you. First question? I'm looking around the room. Here's a question over here. The question, James, is what's the current state of the art for data transmissions, I presume, from CubeSats, and what's a good challenge goal?
So I would leave that to experts in the room that developed the challenge, to begin with Jim in particular, who could probably give you some good numbers to understand what those goals are. I'm not going to try to answer that question directly.
Yeah, I can give a little. Maybe the short answer is that, of course, that's a complex question because it depends on where you're talking from and who you're talking to. So far, CubeSats have primarily been flying in low Earth orbit. In fact, there have been very few exceptions, a handful that I can think of. And so what we're trying to do is advance the state-of-the-art for CubeSats that can communicate over long distances from deep space or from the moon, which serve as models for interplanetary CubeSat communications. And that's going to be a feat that we will be defining here. I think we will be the ones who are breaking the new ground on what those communications data rates and how we're going to conduct those kind of communications are. So that's a short answer. We could go into more technical details, but...
Yeah, I'll add a little bit of color to that and just say that, if you have a CubeSat in low Earth orbit and you don't have a lot of bandwidth requirements, you could pull it off even with an omnidirectional UHF type communication if you're really just looking for, an existence proof that your satellite is alive. And it doesn't require that much power or that much capability. But, as you get further and further away, relying on omnidirectional is quickly going to evaporate and you're not going to be able to pull it off. Then you're going to have to think about S-band and X-band and then eventually KA or KU and eventually laser communication. Each of those steps narrows the beam and thereby reduces the power requirement to send the information back to a distant location such as Earth. But of course, there's major technology hurdles at every step. I think X-band is pretty common at this point for a lot of low Earth orbit CubeSats. It certainly is been demonstrated successfully by multiple organizations. Is that going to be good enough to have high enough bandwidth for deep space? That's highly questionable. Maybe it needs to be something like, a KA or even a laser communications in order to take advantage of the lower power requirements because of the finer pointing of the beam.
There's a question here.
Why now? So after the Derby Derby, what happens next?
So James, the question is, why do the Derby now and what happens after that?
So we always look at technologies that we feel are what we say are at the tipping point. In other words, if we go and demonstrate a technology in space, and this is often true for all centennial challenges, that we see that there's a market potential once an existence proof is in place. So we believe, the Space Technology Mission Directors, after looking at this problem from a small spacecraft perspective, that if we were able to motivate or stimulate a highly efficient communications capability in terms of power and mass and footprint on a small spacecraft in this time frame, that it would enable a vast increase in the market utility of small spacecraft, and with the potential of that communication system actually translating upwards into larger utilization on larger spacecraft as well. So, but there isn't an existence proof out there today that this can be done, especially from distances of beyond lunar distance for a small footprint as a 6U CubeSat. We think that if that were to take place, that suddenly there would be a mad dash to build cheaper, more inexpensive CubeSats, not just for LEO, but also for potentially science missions in the future that would go to other destinations, or even commercial providers of spacecraft to go and visit asteroids mining or exploration purposes. So we think that there's a lot of market out there. We think it is at the tipping point, and we think that it needs an existence proof to jumpstart many competitors to jump in and start competing within this new market space. I would say the propulsion idea is essentially, we think, at the same place without going into detail.
I think we have time for one more question, and then I'll go with the man in the blue there.
Is there going to be any specific process, so if we're developing new technologies, is STMD or other parts of NASA going to be looking at these technologies as they mature, so that, for example, you're a small company here now, people inside NASA know what you have on?
Did you hear that question, James?
It was echoey, so I couldn't quite catch
The
it.
question was, as these teams competing in the CubeQuest challenge develop new technologies, will there be people inside NASA with an eye on that, thinking about how those technologies will benefit NASA?
The answer is absolutely yes, but as with all challenges, the IP would be retained and owned by the organization that actually won the challenge. But we would certainly be paying close attention. We do recognize places like the Science Mission Directorate and even the Human Exploration Mission Directorate within NASA that are really dreaming about sending more capable spacecraft to further destinations and eventually sending people to planetary bodies such as Mars, that we need to have more bang for the buck in terms of spacecraft capability, and that small spacecraft offer the potential of doing many missions that we have always traditionally thought of as only being able to be performed by large spacecraft. But there are these sort of Achilles heels that are out there right now for small spacecraft that we think could be solved by this challenge. If it proves very successful, depending on what comes out of it and the technologies that are employed to solve these problems, we do think that there's a strong upside potential that missions within science or even human exploration might say, let's go and utilize these to perform these missions, as opposed to spending money to a much greater extent on larger spacecraft. And it just really comes down to a gear ratio problem where, a mass at Mars or at an out-of-planetary distance, even a single kilogram, is difficult to get there just because of the propellant it takes to get the distant destination within a reasonable time frame. If some of those missions could be performed by smaller platforms, there's a tremendous upside to affordability that quickly comes into play.
James, that's the end of our time that we have available, and I really appreciate you taking time out of your schedule to be here with us by voice. And we thank you for your time, and we'll keep you informed as the summit progresses and also as the challenge progresses. So let's thank James Reuther.
Thank you, and sorry I couldn't be there today. Business up at NASA headquarters, unfortunately, forced me to be out here in D.C. this week, but I'm glad that you guys are out there, and I'm out there in spirit, if not in person. Thank you.
Thank you.